Okay, so as I said, so you'll see one more. You see one more triangle here, right? So that triangle helps us to compute P2B, this other length. Uh, so can you tell me what P1A is? P1A, this is A. Yeah, P1A is x2 minus x1. Good. What is AB? What is the length AB? You want to find the length AB. So it's y2 minus y1. Okay. So this is x2 minus x1. This is y2 minus y1. So the length P1B would be square by our Pythagorean theorem. So the length P1B would be x1 minus x2 squared plus y1 minus y2 squared. Okay, square root. So this length of this diagonal line. So if I can draw some other color maybe. So length of this line is x2 minus x1 squared plus y2 minus y1 squared. Okay, and the length of this vertical line P2B is z2 minus z1. Okay, now let's put them together to find that the distance will be. So if you use these two distances and apply Pythagorean theorem, you'll see that the distance is what I claimed. Okay. So I hope you understand this. It's basic geometry. If you are applying Pythagorean theorem twice, so to once to get this diagonal length, and once you have the diagonal length, you will use the height to get the total distance. Okay, so this is the distance. Okay, so let's see. So P2B is this length here. Okay, and this triangle. So one of the length is x1 minus x2 squared plus y2 minus y1 squared, and the length is z2 minus z1. So now if you apply the Pythagorean theorem, you'll see that the distance of P1 and P2. Okay. So I'm trying to open some new page. So we see that this is square root of x1 minus x2 plus y1 minus y2 squared. This is P1, this is P2, this is B, and this length was z2 minus z1. Okay, now if you apply Pythagorean theorem, you see that P1, P2 squared is the square of this length plus square of this length, which is x1 minus x2 squared plus y1 minus y2 squared. That's the length of PB plus squared. Next, P2B squared is z1 minus z2 squared. Okay, so this is one length, this is second length. You add them up. This is square of one length, this is square of another length. So that's why P1, P2 is x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared. Okay, questions in this? It's basic geometry. So if you have two points, you can draw these triangles and do Pythagorean theorem. From Pythagorean theorem, you get this length. So that's why you get this whole squaring business. Questions on this? Okay, so it's an important formula. So it's very similar to the, it's basically, if you understand how the two-dimensional formula works, it's simple generalization. Algebraically, there's no difference. You have to simply generalize to 3 dimensions. Okay, so that's fine. So please make sure that you understand the geometry of it, but at the minimum, you at least should know the formula. Okay, so how the formula works and why the formula works. So why the formula works is from geometry. The geometry is through Pythagorean theorem. Okay, so I'll move ahead. So let's see how do you, so an example, for instance, so how will we use these things? So if you have a point 215 and point minus 23, what will be the distance? So let's see. So you subtract the coordinates and take the sums of the squares. So I have minus 2 minus, so P2 minus P1. So minus 2 is one of the coordinates. Next thing is 3 minus 1 squared, and next thing is 0 minus 5 squared, and you take the square root. Okay, so that's what I've written. So minus 2, 3 minus 1, and 0 minus 5. Okay, you subtract those coordinates, take the squares, and add them up. Okay, so that's how you find distances. So is it clear? So that's one basic idea. So in 3 dimensions, so the distance formula changes slightly. It becomes, we have an extra z2 minus z1 squared. Okay. So yeah, you can, this is what, if you simplify, in this case, you get some 6.7, but essentially you apply the formula with those coordinates, you'll get this answer. Questions on this? Is it clear? Is the formula clear? Okay, so please, yeah, so I hope if you solve some problems, you'll know how to use it. Also, I advise you to kind of think about this geometric, what's happening, so to make sure that you really understand why the formula is true. Okay, but at the minimum, you should know how to use the formula. Okay. Okay, so let's move on. So we'll use this formula to do something. So the question, so what is a sphere? So how do you, so we know what a circle is. Circle is something that looks like this. Even a spherical thing also looks something like that in 3 dimensions. Right? So, but what is it? Like, what is the difference between a spherical thing and a most like something like this? A potato like thing. Okay, how do you different? So how do you, what is a spherical thing? So how do you, what distinguishes a sphere? No, I mean, both of them can have the same volume, right? I mean, yeah, so they have volume, yes, but like, how do you, what are, yes. So it's a ball, so it's like a ball, but what does a ball mean? So, so what distinguishes ball from, like, if I squish the ball, that's still ball, but like what's the difference between a normal ball and a squished ball? Yes, so you guys are right. So it's basically all the points on the on a ball basically are at the same distance. Just like in 2D, all the points on the circle are at the same distance. Even in 3D, if you take all the points at the same distance, you get a ball or a spherical object. Okay, so that's kind of the defining feature. It's a set of points which are at the same distance from a fixed point. Okay, so if you take any point and you take some radius and you draw all the points, so if you take any point that you like and take all the points at some distance, like a distance 10, okay, then you get a ball of that or a spherical object of that size. Okay, so that's what is a spherical object. Okay, so okay, so now geometrically is it clear? So the geometry is quite clear, right? Geometrically, a spherical object is just a set of points which are at a distance, fixed distance from this point. Okay, is the geometric idea clear? It's basic. First thing is to understand what is it geometrically. So geometrically, it's just a set of points which are at a fixed distance from where you are. Okay, you should take all the points at the distance from you. If you only take points on the plane, then you can see that although the ball is quite big, if you take only the points on the plane, you get a circle. Is that clear? Instead of taking all the points in the space, if you imagine that if you restrict to the plane, you're only getting some points, and those points will be the circle. So that means that if you intersect a plane, your horizontal plane, with this sphere, you will get a circle. Okay, so the intersection of this plane, horizontal plane, with this ball will be a circle. So you can imagine that, I guess. So this is all the job. So you should, I hope you guys are visualizing it. The visualization is important, main important. So again, the whole course is about visualizing and understanding the geometry and relating it to the algebraic equations. Okay, so geometrically, I hope the idea is clear. You take all the points which are at a distance. So now how do I write the equation of that ball or this sphere of radius, like some fixed radius? I give you some, I say I want you to draw a sphere of radius A with the center x0, y0, z0. How do you write the equation? The equation is quite simple. We write whatever we said, right? So the distance from P1, P2, P0, P1 is this expression, x minus x0, y minus y0, z minus z0. So the distance from the fixed point to arbitrary point on the sphere is exactly equal to A. So you write that equation. So this is the distance between the arbitrary point xyz and our center x0, y0, z0. So the distance is exactly equal to A, right? So that is a defining condition for a sphere. So if you take the squares, you get this equation. Okay, a sphere of radius A passing through x0, y0, z0 has this equation. Okay, so geometrically it's a set of points at a distance, fixed distance. But if I write it in terms of algebra, it becomes this. Okay, this is algebraic. This is algebra. Okay. Questions on this? Is the relation clear? So algebraically, it becomes an equation like this. You should have seen its complete generalization of circle. You would have seen equations for circles. So for instance, if it is a circle, you would not have this z1 minus z minus z0, right? You have x minus x0, y minus y0 squared equals a squared. So that is the equation for a circle, but in this case, it is equation of a, if you have the z coordinate, you get an equation of a ball. Okay. Questions on this? Is the relation clear? Okay, so I noted again here. So basically, this is the equation of a sphere of radius A and center x0, y0 and z0. Okay, so we should know how to deal with this equation. So we should be able to recognize that this is the equation of a ball or a sphere. Okay, so let's do an example. So you want to find the equation, find the center and the radius of a sphere, which is given by this equation. Okay, so let's do that. So this is the equation, and he's saying it's a sphere, but it's not in the form, right? It doesn't look like this. This equation doesn't look like the equation that we have. So what do we need to do? Right? So this equation, if you have given this form of the equation, we can read out what the radius is, what the center is. So, but we don't have. So what do you do? So yes, so we complete the squares. So complete the squares, good. So let's see. So if you complete the squares, so x squared and 3x. So x squared plus 3x plus what? This is 2 times 3 over 2. So 9 over 4. Okay. Plus y squared plus z squared minus 4z plus 4. So equals 3 plus 9 over 4. Okay, so I have to complete the squares. We have to add this whole quantities. Okay, so let's see. What do you get? So if I complete the squares, you have this as x plus 3 over 2 whole squared is the first guy. sorry, plus y squared plus z term is z minus 2 whole squared. So if I do that, you get 21 over 4. So now can you tell me what is the center? What is the radius? Which 4? Oh, so it's plus, what did I do? Okay, so I have a plus 1 in the equation, right? So that's why there's already a plus 1. So that's why, so we're adding this extra 9 over 4. So, or you can think of it as minus 1 on the other side. So it's 4 minus 1. Okay, so it's basic algebra. So you just complete the squares. So you get this equation. And now can you tell me what the center and radius are? Okay, so yeah, the center has to be minus 3 over 2. So you can compare it with the standard equation. So the center has to be minus 3 over 2 and y minus 0, so 0, and z minus 2, so it's 2. What is the radius? So the radius, as this is nothing but 21, square root 21 over 2 whole squared. So the radius has to be square root 21 over 2. Okay, so that's how you do the stuff. So sometimes the equation, it's the, this has to look like this, but it not, I mean, you can write, there are different ways of writing the equation. I can, so for instance, instead of writing it as this x plus 3 over 2 plus y squared plus z minus 2 squared, people wrote it in terms of they kind of expanded the squares. So that's why it became some equation like this. So to recognize that it is of this form, you have to complete the squares, and once you complete the squares, you can read off what the center and the radius is. Okay, questions on this? So for instance, so what is the radius of this? So what is the radius of this sphere? Can you tell me the radius? Yeah, so this is square root 2 squared. So this is just square root 2. So the center is, again, you just read out from what you see. There's a 2 there, there's a 3 there, and a 4 there. Okay. Okay, so if you see an equation, you can directly read off the center and the radius. Okay. So please make, so this is the connection between, so this is, so in your minds, you have this spherical things, but algebraic, so this is the geometry, so but algebraically, you should also have this idea. So x minus x1 squared, y minus y0 squared, plus z minus z0 squared. So this is the radius squared, or whatever. So, okay, so the center is x0, y0, z0, and the radius is r, say r squared. So you have to kind of map these two objects. Okay, so the geometric idea in this case is clear. So you're visualizing all the points in the distance. Distance equals r, right? From x0, y0, z0. And when you do algebra, you have an equation like this. It's a quadratic equation in x, y, and z. Okay, so that's about spheres and 3D systems. So I hope you guys will practice more about the three-dimensional coordinates, x, y, z, how to relate different geometric objects with the equations. Okay, as I said, spherical objects have these quadratic equations. If you want to draw planes and stuff, so you'll have some linear equations. Okay, if you have, write a plane, you get some equation like this. You might have seen something like this in if you draw planes. If you have any plane, it will look like a linear equation. So we'll discuss this later, but I'm just telling you, for every geometric picture, there is a corresponding algebraic idea. Okay, so please, I mean, that's the very point of the course. So please try to consciously try to map these two things. Okay, so they're very different kinds of thinking. Geometric thinking and algebraic thinking are very, very different kinds of thinking. So, but the power comes only if you use both of them together. Okay, so if you understand how they're related, as I said, it's one of the most non-trivial and mind-blowing ideas that humans have kind of built. So you should consciously try to appreciate it and try to figure out what the relation means for everything that you see. Okay. So we'll discuss about this planes later, but like I'm just telling you. So for every geometric thing, there is a question. Which question? Sorry, which question is it? You're asking for this or the previous problem? Okay, so let me. Give me a second. So this was a question. So you have this equation and you want to find the center and the radius of that equation. Okay, so you don't see the center and radius directly, so we have to form the squares and then you'll see the center and the radius. Okay. Okay, so that's kind of the introduction. So really, it's basically the one you think, or if you haven't seen before, is this equation of a sphere of radius something and center something. Okay, so it's essentially coming from the distance formula, and this is also not different if you are used to the 2 dimensions. It's just generalizing it to the 3 dimensions. So all of this first kind of chapter, first kind of part of the chapter 12.1 was about setting up these 3 dimensions and how to visualize things in these 3 dimensions and understanding this distance formula. Okay, so distance formula and making sure that you understand the relation between the algebra and the geometry. Okay, so please review problems. So you'll have a quiz tomorrow in the recitation. So please review all this stuff. So I hope so the homework is already, the online homework is available for you guys to work on. So if you can, yeah, there will be practice problems in the online homework if you guys want to. Also, there are a lot of interesting problems at the end of the textbook. I would advise, if you really want to learn more, you should try to think about all the problems at the end of the textbook as well. Okay, so now the main topic of this chapter, 12th chapter, is this topic of vectors. So how many of you have seen vectors before? Right? Okay, so it's okay. I guess some of you, if you have taken some physics or something, you might have seen vectors. But it's okay. So the idea is quite simple. So we'll discuss the idea of vectors today. So today is the idea of question is what is a vector? Okay. The point of today's discussion is what is a vector. So you want to understand. So you might have heard this word a lot of times. So vector. So what do you mean by a vector? So in a mathematical context, vector is, so you'll see it in a lot of places, physics, mathematics, computer science, whatever. Wherever you take, vector is the most basic mathematical entity. It's something that people talk about all the time. So, but what does it mean? It's quite simple. So let's see what it means. it just, okay, so it has, vector means it has instead of, okay, so what are the things that are not vectors? So numbers, right? So numbers are like, there are, so if I ask you what is someone's height, or what is someone's mass or weight, they are just numbers, right? So some quantities that you see in life are just numbers. So they are some real number, okay? So a lot of quantities that you see are some real numbers. So they don't really, it just simply, you can describe, it's interesting that you can describe a lot of physical things by just using numbers, right? So the height of something, the weight of something, like anything, speed of some object and so on. So you can describe them by just a quantity, that's a number, that's fine. But certain times you might want to describe quantities using more than numbers. For instance, if I have to say the speed of some object or the velocity of some particle, you can move, they're different. It's not just the speed that captures the velocity, you also need to know the direction, right? So in general, if you want to understand how an object is moving and how fast it's moving, you should know how fast it's moving, that's the speed, but you should also know which direction it's moving. You can move along the same speed in different directions, okay? So if you really want to know something about an object that you care about, you also want to know what's the direction in which it's moving. Okay, so the idea is that, it's not enough to keep track of just quantitative information. It's also important to know what the direction is. So for instance, for a speed, you want to know the magnitude of the speed, but you also want to know the direction. Okay, so in a lot of situations, so vector is this way of encoding the direction of quantity that you care about. Okay, so for instance, if you have seen physics, a lot of forces have directions, accelerations, velocities, displacements, a lot of all these things are vectors. If you are used to computer science, every file is a vector of ones and zeros. All websites are vectors. So in some sense, a lot of things are vectors. Okay, so anyway, so let me tell you basically what. So the way we think of vectors now is that it is an object. It's a geometric thing which starts at a point A here and it ends at a point B. So that's a vector. So you start at any point, you end at a different point. So if you draw a line between a starting point A and end at a point B, that's called a vector. Okay, so is this clear? So vector, it means that you start at some point, end at another point, and you get a direction. So because you're moving from A to B. So that line segment moving from A to B, so it should have a direction. So it's different from, like for instance, the segment going from B to A. Okay, B to A is the vector B. Okay, so questions on this? A vector from A to B is written like AB. It's just you draw a line segment from A and end at B. So this geometric thing that you see here from A to B, moving from A to B is called a vector, right? It's something very simple. So you take any 2 points in the space, you move from one point to another point. And you have to tell him what direction you are moving from point A to point B. So if you move from point A to point B, you write it as AB. So that's your vector. Okay, questions about what vector is? It's a very basic idea, so you should try to get it. Okay, if you don't get the idea of what vector is, the whole course it doesn't make sense. It's really about understanding what a vector is. Okay, so let's move on. So as I said, you draw vectors from any point A, any point B. You draw it like this, point A to point B, and you notate it like this, AB bar. Okay. So this is one way to denote vectors. A vector is denoted by A is called initial point, it's the starting point, and B is called the ending point or tail. Okay. So you draw an arrow here. So it's not just a line segment. You draw an arrow to kind of describe the direction of the vector. Okay. So questions about, is the idea of vector clear for everyone? Okay, so it's basically take 2 points from A to B, draw a vector, line segment with an arrow in it. So that tells you that you're moving in that direction from A to B. So that's a vector. Okay, so there is some subtlety about vectors. It's nothing much, but so as I said, vectors are represented by the segments AB, right? So that start at an initial A and terminal point B, and we denote the length as this absolute values of AB. Okay, AB is this geometric thing, right? It's a you should, when you think of vector, you should think of geometric segments. Okay, so the geometric segments, and if I want to know what's the length of that segment, I write it as absolute values of AB. You know what absolute values of numbers are, but here you just kind of write it as absolute value of this vector. So when I write an absolute value of vector, it means it's a length of the vector. So let's me take an example. So if you are on a plane, so I'm at this point, say, and I draw this. So this is say 1, this is say 5, this is A, this is B. Can you tell me what is the length of AB? So this is a vector from A to B. What is the length of AB? Yeah, so it's just length of 4. So that means it's 4. Yes. So when I write AB equals 4, that means the length of the vector is 4. Okay, good. So now let's do one more. So if I have some, so say this is 3, this is 4. So I have A here, P here. Can you tell me what length of AB is? Okay, so this is by Pythagorean theorem, 3 squared plus 4 squared is 5 squared, so the length is 5. Okay, this length is 5. Just apply Pythagorean theorem. Square root 25 is 5, yeah. Okay, so that's the part about vectors. So again, you draw any 2 points in the space. They need not be on the plane. You can take any 2 points from here to here. Like you just from here to there, anything that in the space around you, you draw 2 vectors. Okay, so they need not be in the plane. So you can. So I am only drawing plane vectors, but you can think of this vector could be anywhere. So it's joining any 2 points in the space. So that's a vector AB. Okay, so I hope you understand what is the notion of vector. But the main point about vectors is that we don't, it's another important, okay, so they are, what I wrote are strictly called directed line segments. Okay, so they are line segments and they have a direction, right? So so you should think of them as, they are vectors, but they are also called directed line segments. So it's a line segment from a point to another point. It's a line, it's a segment of a line, but it has a direction. So it's called, that's why it's called a directed line segment. Okay, so but there's a interesting feature. So when are 2 vectors equal, right? If you have 2 distinct line segments, can they be equal? So that's a question. So we kind of define 2 vectors to be equal if they have the same length and the direction. Okay, so this is a very important thing. If 2 vectors have the same length and direction, we call them to be the same, like equal. So they are not the same object, but we call them equal. So for instance, In this picture, so we see that this vector AB and this vector CD are distinct directed line segments, right? But they have the same length. Okay, it's one is basically a translation of the other. You're just moving that line segment to, and you can put, if you move the line segment AB, if you put it on CD, they exactly will match. So all the, even the same thing with OP, all these lengths are the same and all of them are in the same direction, right? So so this AB is a vector, CD is a vector, OP is a vector, EF is a vector. So all of them are different quantities, different line segments. But what we say is that if they have the same direction and magnitude like this, so all of them have the same direction, they are parallel to each other. And if they have the same magnitude, so in this case, they have the same magnitude, they have some length. So basically one of them is a translation of the other. You move them, you take one line segment AB, you move around without changing the direction, then you get the other line segments, right? So if that is the case, you call all these things as the same. AB equals CD equals OP equals EF. Okay, so that is what you mean by equality of vectors. Is the notion of equality of vectors clear? So let me draw something. So if you have a vector like this, so this is AB and the vector, okay, so CD, do you think these vectors are equal? Okay, what about this? Right, so AB, I hope it looks like they're equal. AB have the same length and direction, so they are kind of equal, but that's not equal to EF. EF is completely has a different direction. Maybe the length is the same, but the direction are different. Okay, so vectors are equal if length and direction match. Okay, so this is the basic thing. If the directions don't match, so you can have two vectors which have the same length. For instance, this is one vector, this is another vector. Say they have the same length, right? Say they have the same length, but even then they are not equal. The length is the same, the vectors are not equal, but the lengths, the absolute values, the lengths are the same. Similarly, you can have the same direction, but you need not have the same length, right? So AB is not equal to CD. Okay, so that's, so if you want the vectors to be equal, you need both the length and the direction to be matched. Okay. Okay, so that's the notion of equality of vectors. So what does it mean? So it means that a same vector, so two distinct line segments at different places can correspond to the same vector. They can be equal. Although they look different, right? You're moving from here to here or moving from here to here. So they're distinct things. But if you only care about the direction and the magnitude, right? You don't care about the starting point, then that's what you call a vector. So vector is something where you forget the initial point. You only care about the length and the direction. So you can move, so you kind of this vector, and because this vector is the same, you can move all the vectors to the same point, and you can then measure if they're equal or not. If you want to see if these two things are the same, move this vector till here and see if they are matching or not. So if you So if one vector is here, if you move the other vector and I get a blue vector which is along the same direction and is matching, then they're equal. If I move and you get something else, then they're not equal. Okay, so that's how you can compare. So if you fix one vector and you move the other vector so that their initial points match, and then you can see whether they're the same vector or not. Okay, so that's some basic information. So yeah, so the vectors, as I said, you don't keep track of the initial information. So different vectors can have the same, different line segments can be the same vector. That means that point where you start doesn't matter. So you don't keep track of the initial point. You only keep track of the direction and magnitude when you talk about vectors. Okay. So again, so some notational aspects. So when you draw vector, so when you denote vectors, we denote them by boldface letters, U, V, F here. Okay, this is some standard notation for vectors. This is how I'll do it. For instance, in a textbook, and when you see it typed somewhere, this is how vectors are denoted. But if in some other notations, for instance, if you have to denote the vectors by hand, you put an arrow on the U, V, F. Okay, so vectors are denoted by an arrow on the top of U, V, F. Okay, so you can do both, but when you write with hands, you do it with a little arrow. When you type it or you take it, you actually do it with this boldface. So both of them are the same notation. So if you see, some people might be using this notation, some people might be using this notation. So you should be used to it. Okay, so in most of my notations, I'll be using this boldface letters. So V. So V is this vector PQ. So if it is vector PQ, say, so that means I'm caring about this line. So this is the vector, sorry, the direction PQ. If I want to understand this vector, is the same thing as understanding this vector is equal to every other vector. I can shift that vector to so that the P becomes the origin and you get this other vector. So that vector and this vector in this case are the same vector. Okay, because the vector PQ and the vector O say R, so this point is R. So both these have the same direction and same magnitude. So both the vectors are the same and they are denoted by this bold face V, for instance. When you write with hand, I write it as just arrow or V. If I write it with computer, I use bold face V. Okay, so this is basically about the notation. Okay, so is the geometry of vectors clear? So the basic geometry is just you have a direction and a magnitude, and you don't care about where you start. If you can move and you can see that you have the same direction and magnitude, they are the same vector. Okay. So questions about this? Okay, so now let me move on. So this is the way of giving components. So we saw what vectors are geometrically. Now this is algebra. So you want to understand vectors algebraically. So how do I represent a vector algebraically? So it's quite simple. So if you have a vector, and if you assume that the endpoint of the vector, one endpoint of the vector is origin, then there is second endpoint. The second endpoint will have some coordinates. You denote the vector using those coordinates. Okay. So take your vector to the origin, and then you see the coordinates of the head of the arrow or the vector. So if the coordinates are v1 and v2, you write you call those v1 and v2 as the coordinates of the vector or the components of the vector. And similarly, if you have in 3 dimensions, you'll have 3 coordinates. You'll call v1, v2, v3 as the coordinates of the vector. Okay, so So before I do this, so can you tell me what are the coordinates of this vector or components of this vector? Components, guys, are you here? Yeah, so the components is just, yeah, so this OP is just 1 and 2. So we put these like less than or greater than kind of signs. They're called, yeah, angle, left angle and right angle. So instead of putting a kind of nice brackets, you do this kind of bracket notation. So yeah, so that's it. If you have the coordinates 1 and 2, you put it at 1 and 2. So what about this vector? So if you have, this is 1, 2, this is 5, 6. So what is, how do you denote this vector? So this is A, this is B. Can you tell me what are the components of this vector? Yeah, so you should put, so this is the standard notation. So we should always put 1 and 2. Okay, why is it 4 and 4? Why is it 4 and 4? Yeah, so one way, there are different ways to do it. So this, this is 4, this is 4. So that's why this is 4, 4. Or as I said, another way to think of the coordinates is you draw, if you translate this vector and draw, this point will be 4 and 4, right? If I translate this vector to the origin, so I have to subtract 1, 2 from everything, so that coordinates will become 4 and 4. Okay, the translation will have coordinates 4 and 4, or you can draw, you can see the components to be just, if this was 0 and 0, this would be 4 and 4, right? With respect to A, B has coordinates 4 and 4. With respect to this origin, it has coordinates 5 and 6. But if with respect to A was your origin, the coordinates of 5, B would be 4 and 4. Okay, so let me do one. What about if I have, say, P is 1, 2, 3, and like Q is 2, 3, 4. What is the vector? Do you have to include the letters I and J? We'll talk about I and J. For right now, it's 4 and 4. ILJ, I will talk about it sometime. Okay, so now, yeah, the components are, yes, 2 minus 1, 3 minus 2, 4 minus 3. This is 1, 1, and 1. Okay, so what about the vector QP? Can you tell me what the vector QP is? What is the vector QP? As I said, vector PQ and vector QP are not the same thing. They are like along the same direction, but they're different vectors. This is PQ and this is QP. Okay, so they have, yes. So you have to change the signs. It's minus 1, minus 1, minus 1. Okay, so I hope you guys got the basic idea. So the geometry aspect is just these directed line segments. And the components or the algebraic components slash algebra is if, yeah, so you write x2 minus x1, y2 minus y1, z2 minus, right? So if this is x1, y1, z1, this is x2, y2, z2. The vector from x1 to x2 would be, you subtract the coordinates, because with respect to the first point, the second point will have this much as the coordinates. Okay, so that's the basic algebra, idea, the geometric idea and the algebraic idea. I hope you should. So as I said, it's important to keep track of both the ideas. Okay, I'm stressing this a lot because as we move on, we'll be using both of them comfortably. If you are not used to one kind of thinking, things will, and you're only used to one other kind of. If you're not used to both kind of thinking with the same familiarity, you'll have some issues. So we should so make sure that you understand the geometry of it and you also understand this algebraic way to understand these vectors. Okay, so we did this. As I said, yeah, so this is something we already seen. So if you have point x1, y1, z1, x2, y2, z2, the components will be just, so pq, if this was 0, the q coordinates would be this much. With respect to p, the coordinates of q is that you have to move x2 minus x1, y2 minus 1, and z2 minus z1. Okay. Okay, can you tell me what is the length of the vector? The length of the vector is, again, so if you v is v1, v2, v3, right? By our Pythagorean stuff, v1 is x2 minus x1, v2 is y2 minus y1, v3 is z2 minus z1. So the length of the vector v would be just v1 squared plus v2 squared plus v3 squared, square root of that. Okay. Is it clear? So by Pythagorean theorem, the length of the vector, because the coordinates are x1, y1, z1, x2, y2, z2, this is the length, but that length is exactly equal to v1 squared plus v2 squared plus v3 squared. So let's see. So what is the length of the vector v equals 0, 3, 4? Can you tell me the length of this vector 0, 3, 4? So I can write v hat. Okay. So this is just, yeah, so square root of 0 squared plus 3 squared plus 4 squared. This is square root of 25, which is 5. Okay, that's it. So if you want to find a length, take the squares of these coordinates or the components and square them up and add them up. So this is just coming from the distance formula. Okay. So these are like the 0, 3, 4 are the kind of the coordinates. So hence, right? So these are the, if this is origin, this would be 0, 3, 4. So that's why the length would be sum of the squares of this coordinates. Okay, so that's the length. So now there are certain other things that we need to know. So first thing we learned about these vectors, geometrically what they mean, and algebraically their components and stuff. So now let's move and study some algebraic things. So the question is, how do I add vectors, right? So if I have two vectors, u and v, how do I add vectors? So there's a vector, so pq, and say there's a vector qr. So what is the sum of these vectors, right? So by definition, okay, if you have a vector to p from p to q, and if you have a vector from q to r, the vector is essentially from p to r. So this is called the sum or the resultant, okay? So pq, if you add pq to qr, you get this vector which is just pr. So is this clear? So how do you add vectors? You just, it's most obviously pq plus qr is pr. Okay, now can you tell me what is PQ plus QR plus RS plus ST? Can you tell me what is PQ plus QR plus RS plus ST here? I want to add this vector plus this vector plus this vector plus this vector. Yeah, it's simple. So geometrically, you just add PT. Yeah, so that's a PT vector. So you close and you get this PT. Okay, so that's it. So geometrically, it's quite simple. So is it clear? So what is addition of vectors geometrically? So is the geometry clear? It's very obvious, right? So you put things some things together. It's AB and BC. Then you get it's nothing but AC. Okay, that's the sum. So AB plus BC is AC. Okay, so now let me ask you some questions. So the simple. So, but if I have AB and I want to add CD, how do I add AB plus CD? How do I add AB plus CD? Yeah, so geometrically, I'm not able to add because I can't close the thing. So you put tip to tail. Yes, that's the idea. So I just move CD to here because as I said, vectors can be shifted, right? So there's no difference between this vector and say, assume that there's no difference between this vector and this vector. I can shift the CD so to say some B E, okay? So AB plus CD is equal to, because CD is equal to BE, right? As I said, vector CD is the same thing as vector BE. So AB plus CD should be equal to AB plus BE. Okay. So because CD is the same vector as BE, it's the same direction, same length. So I get AB plus CD is nothing but AB plus BE. Now I can add the vectors. Now the addition is nothing but AE. So this is nothing but AE. Okay. So that's how you add the vectors geometrically. If the head of one thing and the tail of other thing kind of match, you can directly add. If you don't, you just move a little so that you you translate your other vectors so that the tip and tail of the vectors match, and then you can add the vectors. So questions on this, adding vectors? So geometrically, it is literally, if you have vectors, it's quite easy to add. Like if you already have head and tail of neighboring vectors are matching. So this is a basic picture that you should remember. AB plus BC is AC, and once you have this, we can add vectors. Okay, so that's what he's saying. So if you have U and V, this U plus V is the vector. And if you have U and V, and I can't add the vectors U and V directly, I have to translate V so that V kind of matches. So the translation looks like this. Now when you add, the vector will look like this. So this is U. Okay, so V plus U will be this vector, the yellow vector. And similarly, I can translate V as well. It doesn't matter what you translate. So v plus u plus v will also give you u plus v. So you see that u plus v is the same thing as v plus u. Okay, there's no difference between adding u plus v and v plus u. They give you the same vector. Okay, so that's the geometry of it. So let's move on to some algebra of the vector additions. So I hope the geometry is clear. It's this way of shifting, and you see a parallelogram here. When you shift, you see like a parallelogram. This is a parallelogram, right? The shape is called a parallelogram. So that's why this kind of adding is called a parallelogram law. Okay, it's called a parallelogram law. So the geometry, whatever I described, is called parallelogram law. Okay, but now how do I add them algebraically? The algebraic version of addition is quite simple. If I have u is v1, v2, v3, u is u1, u2, u3, the sum of the vectors is just you sum the components. So if you want to count the first component, you add the first component, second component, you add the second component, third vectors, you add the third component. Okay, so let's see. So if u is 1, 2, 3, v is 1, 3, 2, what is u plus v? Can you tell me what u plus v is? Right, it's 1 plus 1, 2 plus 3, and 3 plus 2. So which is 2, 5, and 5. Okay, what about u minus v? I didn't tell you what minus is, but it's similar. Can you tell me what u minus v is? You subtract components, right? So 1 minus 1, 2 minus 3, 3 minus 2. So which is 0, minus 1, and 1. Okay, so that's it. So in components, it's quite simple. It's a list of numbers. You do it by component. First, you forget that they're vectors. All you need to do is you do it by component. Okay, so a lot of stuff with vectors in algebra is quite simple. So vectors using algebra. So this is algebra. So algebra of vectors. With algebra, the vectors it's easy to. There's nothing much. Okay. Okay, so we'll continue more stuff. So for instance, you can also multiply a number to a vector. So 2 times 1, 2, 3 is nothing but 2, 4, and 6. Okay, so we'll continue with other aspects of vectors, but please practice something about 3D coordinates and what vectors are. Okay. So, okay, so if you have any questions, you can hang around and ask me questions. And if you want to have suggestions for how the course has to go or anything else that you want to speak, just please stay around and tell me anything that you have.
Okay, thank you, Professor.
Yeah, good. Thanks.
Could you just go over vector subtraction real quick?
I didn't write the vector subtraction slide. Okay, so I'm just saying, you mean the previous one, or this example?
Yeah, for u minus v, it would be, okay, it would be that. It wouldn't be v minus u. You wouldn't take the terminal and divide it and subtract it from the initial?
Yeah.
All right, thank you.
Yeah, okay. Okay, so sections, so it's, I couldn't, I mean, I didn't even finish 12.2. Yeah, so we'll do 12.1 and 12.2 essentially for the quiz tomorrow. 12.3 will start in the next class. My email you should see all the details on Canvas. Okay, so this is my email. Oh, today is the Monday schedule. So my office hours are on Tuesday and Friday, but today is Monday schedule. So I might not have any office hours today. Responsible for any readings before next class? Yeah. So I'll post the readings. So it should be 12.3 and 12.4. Oh, the quiz today, the quiz was a reading assignment. The quiz that you see that was due before the lecture was a reading assignment. It was basically, it was nothing much. So the quiz, so you'll have reading assignments before every lecture. Okay, right? So there will be one reading assignment that you need to submit before the Thursday's lecture. It's for you, yeah, you're expected to read through the textbook because the online stuff, we can't, there might be some things, if things are not clear, it would be helpful if you actually read something before. I'll post the slides, yeah. You should see all the slides on Canvas modules, the slides and the work as well, the other notes. So you'll see it on Canvas. When will I post? I'll post it after the lecture, like in the next few minutes, yeah. For the quiz, just 12.1 and 12.2. I mean, okay, so if the TS said it's okay, it's okay. So see, because you have some issue, like specific issues, yeah, so it's fine if you can attend that. Or you want to kind of change. Okay, so just send me an email. I'll respond to that. Thanks. So someone else is asking something. Sorry. What sections do we need to cover? 12.1 and 12.2. Onboarding quiz. So there are two. Onboarding quiz is just for practice. So please make sure that it's not really for credit. You should do one of the onboarding quizzes. If you didn't do quiz 0, that's fine. You should do at least quiz 1. I mean, it's reading assignment is like, yeah, counts. So all the assignments together will count for some percent, but each assignment is not that much. It might be like 1/100th of a point. I don't know. So yeah, so it doesn't really count that much, one specific thing, but I can, if you want time, I can give you time to answer it. 12.1 and 12.2. We didn't start 12.3. So the quiz will be on 12.1 and 12.2. 12.3 and 12.4, you're supposed to read before the next lecture so that you'll be prepared for the next lecture. Will we have suggest problems answered? So I didn't get you. What do you mean by suggest problems answered? Sorry, can you tell me what the question is specifically? Like, you mean, oh yeah, so I don't have the answers. If you have something, maybe you should ask the TA if you have specific problems where you want answers. There are say, for some of the problems, you'll find the answers at the end of the textbook. Okay, so any other questions? Yes, I can answer specific questions during office hours. Uh, yeah, so okay, we can talk for some time if you have some problem right now. So because I don't have office hours today, so this because of the change of schedules, but I'll have it on Friday. So, but yeah, if you have something now, I can spend some time discussing now. But otherwise,
Yeah, so the problem I had was 12.3 in the textbook,
yeah.
number 19.
Okay, give me a second. So do you have, can you share, let's see, 12, give me a second. What's happening? Okay, let me get the textbook, sorry. Where on Canvas can you see the recordings? There is a Canvas module section where, so you can see it on Zoom. There should be something called cloud recordings. You should be able to see there, just somewhere on the Zoom tab, or you can, I post an explicit link on the Canvas modules. Yeah. So wait, what was the question? Sorry, can you tell me the question?
Number 19, it says sums and differences. 12.3.
3, 19. Okay. Okay, so you were asking when do you expect the vectors to be orthogonal to each other?
Yeah.
Okay, so but have you, so we haven't discussed this in the class yet, but have you read stuff about other dot product and so on?
Yeah, I was able to do all of the other problems.
Okay.
It's just that one was confusing to me.
Okay, so let's see, right? So let's see when, so you know what dot product is, right? So
Yeah.
A dot B, it's like it tells you it's the length of A, length of B times cosine theta. So, okay, it's a main.
I can't see your screen.
Oh, okay, sorry, something happened. Okay, can you see it now?
Yeah.
Okay, okay, so the dot product can be related to the angle between the vectors. So this is something we'll discuss. Do you know this before?
Yeah, I read the chapter.
Yeah, so A dot B can be written in terms of the lengths of the vectors and the angle between the vectors. So he's saying the angle between, say, V1 plus V2 and V1 minus V2, right? They are orthogonal. That means they're at an angle of 90 degrees. So what will be A dot B? So what will be the dot product?
0, right?
Yeah, the cosine of theta is, yeah, cosine pi over 2, which is 0. Yeah, so can you now tell me, so let's see what will this give us, right? So, so this is V1 dot V1 plus V2 dot V1 minus V1 dot V2 plus V2 dot V2. Sorry, minus V2 dot V2 equals 0. Okay? Is this clear? I'm just multiplying it out. A plus B dot C plus D. It's just like,
yeah.
I can do A dot that plus B dot that. So if I multiply it out, you get this. And things get cancelled. You get V dot V minus V2 dot V2 equals 0. Okay? Is that fine?
Yeah, that's clear. Thank you.
So that means V1 equals V2. I mean, the length of V1 equals the length of V2. because v1 dot v1 is nothing but oh yeah, so someone else has a question. Yes, I'll after this I'll do your question. Please stay around for some time. So v1 dot v2 is nothing but length of v1 square. v2 dot v2 is length of v2 squared. So length of v1 equals length of v2.
Okay, thank you.
So that means so if you have two vectors whose length is the same, okay. Now if you take the sum of those vectors, you get something like this. If you take the difference of those vectors, so if you take the difference, you'll get something like this. And they will always be at 90 degrees, yes. Okay, so that's, okay, what I showed you is a very algebraic way to show, right? If the length of v1 equals length of v2, then they are perpendicular, but you can do it geometrically as well. Do you know how to do it geometrically? So, so this is, you should do some angle. So if you remember your school geometry stuff, you can show that this is 90 degrees. So let's see. So this is length A. So this, so if this is theta, right? This is 180 minus 2 theta. So this is 2 theta. So this will be, these angles should be the same. So this will be 180 minus 2 theta over 2. This will be 180 minus 2 theta over 2. So the length of, so 180 minus 2 theta over 2 plus theta is nothing but 90. This is a direct geometric way to say it without doing the. So did you get what I'm doing? So because these lengths are equal, so the angles, these angles will be theta and theta for some theta, right?
Okay, it makes more sense to me algebraically.
Okay, that's fine.
I can understand it geometrically.
Yeah. Which one?
It makes more sense algebraically, but I think I understand what you mean.
Yeah, okay. So you can chase things geometrically, like you can see why there's 90 degrees without doing all that. Yeah, okay. So it's using your whatever high school geometry kind of stuff. Okay. Any other questions?
No, thank you. Thanks.
Okay. Yeah. Okay. Okay. So Cassandra, are you here?
Hi, yes.
Hi. Yeah. So can you tell me? So you have 12.2, 41. Okay. Give me a second. Okay. So did you already read the chapter?
Yeah.
Okay. So you have, as I said, we didn't still discuss what these vectors are. So u is 2i plus j, and v is I plus j, right?
Yeah.
You have these two vectors, and three vectors actually.
Yeah, there's W.
I minus z. So you want to, he's saying that there's a relation like this. U is a v plus b w, right?
Okay.
So he says there is some relation like this, and we don't know what a and b are. We have to find them, right? That's the question. Is that the question?
Yeah, they want to know. Yeah.
Yeah. So now just write down all the information that you have. What is u? U is 2i plus j, right?
Mm-hmm.
A times v is I plus j plus
and
b.
then plus b I minus j.
Yeah. Okay. So now, so multiply things out. So this is 2i plus j here, and on the other side is ai plus aj plus bi minus bj. Okay. Right. I just multiplied a.
Yeah.
Okay. So now I put these things together. So ai plus bi is a plus bi. Hi. Sorry. Aj minus bj is a minus bj. Is that clear? this step clear? Hi? Excuse me? Can you hear
Oh,
me?
yeah, sorry.
Yeah.
Yes, it's clear.
Okay, now do you know what you need to do? So there are these two vectors and we know, so you have to compare. So A plus B would be 2, A minus B would be 1, right? So I'm comparing the left and right sides.
Oh, yes, because it's 2i plus, okay. Okay, yes, that makes sense.
Okay, now you just solve for A and B.
Yeah.
So A is 3/2, B is half.
Okay. Thank you.
Yeah, so any other questions?
Oh, no, that was it.
Okay, yeah, thanks. See you next time.
Thank you. Have a nice day.
Yeah, thanks.